Hi, my name is Paco Nathan. I'm with O'Reilly Media, and we're here at the O'Reilly Artificial Intelligence Conference in New York City. And today it's a great pleasure to get to talk with Gadi Singer, who is VP of Artificial Intelligence Product Group and also General Manager of Architecture at Intel.
Hi, good morning.
Gadi, very good. Good to speak with you. Now, I have some questions following up from your keynote. By the way, excellent keynote this morning.
Thank you.
What is DL Boost, and why does it make a difference to your customers? Can we talk a bit about that?
So DL Boost is about enhancing the hardware, the CPU hardware, to operate better, even better, on deep learning applications. The hardware had already AVX to do vector instructions that are very effective for that, but we look for ways to increase the efficiency of doing the acceleration for deep learning within the CPU. And DL Boost with the VNNI, the neural network instruction addition, allows a significant enhancement of the hardware. And it gives, for some applications, a 14x boost in some operations, which is very significant. And the fact that it does that boost within the stream of instructions that is executed on the CPU is very effective for the overall application.
Excellent. Is that more in the inference side, or is it?
It can be used in both training and
great.
inference. There are some enhancements for low precision, and those enhancements probably are more applicable on the inference side, but overall, the cascade lake can be used for either training or inference.
Excellent. Well, can we touch on more about the Cascade Lakes, the processor, and talk about an example of implementation of that, and in particular, how has DL Boost helped out with this kinds of use cases?
So the second generation Intel Xeon Scalable processors, which is the Cascade Lakes, is really upgraded to support those workloads. And an example of that is recommendation systems. The highest percentage of cycles on deep learning compute goes to recommendation systems.
Interesting.
And those recommendation systems are integrating some compute that is sequential and can run very well on any CPU, but it also has some intensive operations on vector and matrices, tensors, and the ability to increase the performance of those vectors and tensor activities very close within the same CPU as the other operation can help recommendation system achieve excellent results.
Wow, fantastic. Also, can you explain the shift into more inference, which you see across different industries, and how Cascade Lakes will address this and help customers to achieve better total cost of ownership by extending the Xeon platform? I know that it's already being used for AI inference, but even if models were trained on GPUs, how is this being used now?
So first, on the transition to inference. About 3-4 years ago, the deep learning technology was at a stage which was more of exploration, finding out what the technology can do, proving its results. And what happened over the last 3 to 4 years is that it is being readied for major deployment. There are multiple companies that acquired the skill set, the required skill set, and integrated those technologies into the line of business applications. And what we're seeing today, as of 2019, is a ratio of maybe 4-to-1 between inference cycles and training. We can see it over the coming years going to a ratio of 10-to-1. So inference is becoming really the focus of a lot of the deep learning activities. And regardless of how the model was trained, the way it is captured in one of the deep learning frameworks can be mapped very optimally to Xeon. And when it is happening, you need to run this mix of CPU activities as well as tensor or vector intense activities. And the enhancements being put into Cascade Lakes allow to do that part very well. And it allows something very important to the customers. Our customers have major investments tuned, optimized over many years to the Xeon environment. And when they use AI, it's not a new application. It's enhancing whatever they're doing for their line of business with AI capabilities. And having this level of integration allows them to protect and extend all this investment and give state-of-the-art performance and capabilities on deep learning.
Fantastic. It's really only, 7 years out now from maybe, I guess, more like 6 years out since the AlexNet paper came out.
That's right.
It's fantastic to see how much tooling at scale, industrial scale, has happened in such a brief period of time.
That's right. And this is the short history of deep learning in action. And you start with AlexNet. You start with the cases of doing ImageNet, and showing that a machine can identify objects almost at human level and then better than human level in some object recognition. And since AlexNet, we had several generations of improvement and of capabilities. And the latest topologies, the latest algorithms are creating a mix. If AlexNet was more pure doing matrix operation and convolutions, the new, more sophisticated models have combinations of activities, and the Xeon and the cascade lake framework allows this hybrid activities to be operating within the same system.
Interesting, a much more heterogeneous, mix of needs.
And this is also going, if you look at AlexNet, the origins were in proving that things can be done differently on images.
Yeah.
But if you look at the use of deep learning today, images is probably the third most common usage. The most common usage is recommendation system, followed by speech recognition, NLP, natural language processing, and then you've got image recognition. And we need our solutions to be very effective in all those families of deep learning.
Fitting that general case.
Yes.
Excellent. Now, can you also talk about specific implementations of AI moving into main lines of business for the types of compute that are needed in mainstream business? So I can imagine that there's much lower latency, there's needs to scale. How do these fit into the requirements for Cascade Lakes?
This is another change that help CPUs, Xeons really shine. Because in the original usages, it was primarily about batch. So there were small pieces of data with large batches to create the efficiency. What we see today is much more focus on latency. We see the data sizes growing up. So the Xeon and Cascade Lake, with its focus on latency, with the ability to do it very well, with the large memory space, is very well equipped to deal with those new usages.
Excellent. I can imagine, in particular, the larger memory spaces are quite an enhancement for performance.
There are several customers that just could not fit their model in a GPU. And the large memory space of Xeon, and with the ability to do a multi-node, very effective multi-node scaling, was a key factor, sometimes an enabler for them.
Fantastic. Can you expand on the scenarios where dedicated accelerators are needed to supplement this kind of inference? I guess because of continuance and intensive inference processing in particular.
So one of the most demanding tasks in deep learning is to do arithmetic on multi-dimensional large arrays. Those are called tensors. And part of what is being done is just having those tensors multiplied, some operations on them, and convolutions. And those very specific operations can benefit from acceleration on a machine that's designed for that. And this is where the accelerators come into play. The accelerators are much more narrow and focused in the things that they do, but they do those things very well. And in particular, we have the Nirvana neural network processors that are coming in 2019 to production. We have the NNPL for learning or for training. So the NNPL 1000, which is codename Springcrest, and we have the NNPI for inference, NNPI 1000, which is Spring Hill. And those are targeted, dedicated acceleration. So they do the task of the tensor arithmetic very, very well. And we build systems that are really the overall system is integrating the strength of the host with offloading the necessary deep learning portions, or those intensive tensor operation to the accelerators.
Oh, fantastic. I imagine that finds use cases far beyond deep learning as well. I mean, there's a lot of general case for this kind of math being accelerated.
That's right. And the ability to do those activities primarily on tensors, on those large multi-dimensional arrays in science and in some of the big data areas is very promising.
Oh, fantastic. Thank you, Gadi. Very good speaking with you today.
Thank you very much.